All right. Well, welcome to Intro to Machine Learning 1, DS44, Lecture 9. This is Professor Wu, and this is a lecture for a course in Northeastern University. So today we're going to go over how you can recognize the most commonly used distributions and basically know when to use them. So in lecture 6, I really emphasize that if you can find the probability density or the probability mass function, if you can find that function, it is really, really useful. With discrete cases, you can just make them into tables like this, especially when you don't have that many variables, and you can just essentially know exactly the probability of any event. But let's say we don't have the probability. Instead, we are going to have the data, right? So today we're going to talk about if we have the data, can we approximate the probability distribution, P of x? Can we approximate this function? Okay, how do we go about doing that? And okay, so today we're going to basically discuss the most basic ways of how to estimate the probability density function. Right? We're going to kind of go over like the most basic ones. So like last time we went over histograms. Right? This time we're going to identify the probability distribution via the mean and the variance. You'll see what I mean by that. I think in a future lecture we'll do this thing called maximum likelihood as well as kernel density. But this is what we're going to do today. So these are the distributions. So this is called exponential, normal distribution, uniform, uniform. This one is uniform continuous, uniform discrete. This one is Poisson, Bernoulli, and categorical. So these are the they're obviously a lot more distributions than what I have shown here. But these are some really basic ones that I think if you're going to start anywhere, you should definitely know these ones first. Okay, so Bernoulli distribution. This is probably the easiest one. This is a discrete distribution where the outcome is only two outcomes. Like who's going to win the soccer match? Team 1 or 2, right? There are only two possible outcomes. Is it going to rain today? Yes or no, right? Will the student pass or fail? So all of these are just two possible outcomes, and that's called the Bernoulli distribution. So for example, in your life, let's say you've gone 100 dates, 20 of which were good and 80 were bad. So what's the probability distribution that describe your dating history? So that's like an example. And this probability distribution, Bernoulli looks like this. So the way it works is that since the outcome, right, x can only be good or bad. So we denote them by 0 or 1. So x can only be 0 or only be 1 and nothing else. So 0 is bad and 1 is good. So imagine if the probability, so in this case, for example, if you went on 100 dates, 20 were good. Therefore, the probability of a good date is 20 over 100, which is, 1/5. And then the probability of bad date is 1 minus 1/5, which is 4/5. So that's the probability of you having a good date is theta. Like probability of 1, basically. And the probability of 0 is here. So now we know that like the probability of you going on a good day is 1/5, and then 4/5 for a bad date. Let's put these into the function. So this is the probability distribution now, P of x. So what is the probability of 1, which is having a good day? Well, you're going to put a 1 here and a 1 here, which means that this is going to be a 0. Anything to the power of 0 is just going to be 1. So this will be 1. anything to the power of 1 is just itself. So therefore, the probability of you having a good date. Now, probability of you having a bad date. So it's probability of 0, right? So you're going to, in this case, you're going to put a 0 here and a 0 here. Therefore, 0 here is just going to be 1, and 1 here is going to be 4/5. So that's the probability of bad day. So you're essentially, you have two outcomes, right? You have two outcomes, 1/5 and 4/5. And you, by picking 1 or 0, you're picking this outcome or this outcome. That's what this equation is saying. So that's the Bernoulli distribution. Okay. Uh, I think I showed it here. Yeah, you can only have 0 or 1. Therefore, it's either 0 here, 1, 0 here, or 1 here. Nothing else. And by doing that, you can essentially pick out like the probability. So with this, I mean, as long as you know theta, right? If you know theta, basically you have the distribution. So the key is to get theta. Now let's take this probability distribution we have here, Bernoulli, and calculate the expectation. So if we calculate the expectation, we went over last class that it's x is the summation of x times p of x. Okay, so well, x can only be two numbers, 0 or 1, right? They're only two. And then 0 is just going to be 0, right? It's just going to be gone. Therefore, it's just 1 times the Bernoulli. And this 1 minus 1 is going to be 0. So that cancels out. Therefore, it's just equal to theta. So what that's telling you is theta is the expected outcome, right? So if you were to calculate the expected expectation of this data, you're going to get theta. And once you have theta, you essentially know the probability distribution. So in the previous example, right, what is theta? Well, we can approximate it. Theta is approximately the average. So you'll just have the average of number of good dates, right? So let's say this 1 over the total number of dates, and then you sum up all the dates. So you'd be imagine if it's like good, bad, good, and therefore all the bad is going to be 0. Therefore, you're summing up the number of good because all the bads are 0. So basically, this is telling you it's number of good dates divided by total dates. So this is the expectation. This is the expectation of. So this is the like how many good dates you expect, and this happens to be the value of theta. So what is good about this is once you calculate the expected value theta, you now have the distribution. You now have this function. So getting this function wasn't that hard. Like you just need to know what the theta means. Once you know what theta is, you calculate it, which is just the average of number of good dates. So likelihood you're going to have a good date. And then once you have theta, that's the equation. You plug the number in there. And when you plot the histogram, you'll look like this. So here's what the number of good dates versus number of bad dates. So Bernoulli distribution only has two outcomes. Okay, then you'll see two bars in a bar chart. Okay, now that we have the Bernoulli distribution, that's only two if you have two possibilities. What if you have multiple possibilities in more than two? Well, that is called a categorical or the multi-nomial, multi-Newly distribution. Okay, so categorical distribution, basically you have more than two outcomes. So it could be three outcomes. What's the weather like today? Rain, sun, clouds, snow. So there are four possible outcomes. Right? Who will win the election? Candidate A, B, or C? Which number will the unfair die land on? 1, 2, 3, 4, 5, or 6? So now it's more than two outcomes. So an example that you could use to model this is, let's say you survey 100 people about how they will react if their father dies. 75 says that they will be extremely sad. 15 says they will be sad. And 10 will say that they will not be sad. So how would you then mathematically model this? Well, previously we have 1 theta and then 1 minus theta. But over here, you have three cases, right? There are three cases: extremely sad, sad, and not sad. So these are the three different cases. That means all you need is theta 1, theta 2, theta 3, x1, x2, x3. So in this case, the x is a vector, right? So x is a vector, x1, x2, x3. And when you have categorical, one of them will be 1 and the rest of them will be 0. So let's say x1 is extremely sad, x2 would be sad, and x3 would be not sad. And therefore that's what the equation is going to be like. P of x is equal to this, and since, depending on the number of category, in this case there are three category, so we're going to have theta 1 x1, theta 2 x2, theta 3 x3. So this right here is the probability of extreme sadness. This is regular sadness, and this is not sad. So this is right here, this is the probability distribution. So what you will input into x is a vector of x1, x2, x3. So let's say I input a vector. So if you put 1, 0, 0, that's equivalent to here, 1, 0, 0. So cancels these two out, right? And then keeps this one. Now you have 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0. In that case, you're going to get this probability. So the function for the categorical looks like this. And you can get each one of these also through the averaging. So let's say we previously see that you just take the average. Now, what you do is you add up the total number of cases of occurrence divided by the total number of samples. So for case number 1, it was how many people would be extremely sad? 75. So it'll be 75 divided by 100. And then that's for case 1. And then for case 2, it was, I believe, 10 out of 100. And so on and so forth. Okay. So this is how you would get theta 1, theta 2. And once you have theta 1, theta 2, once again, it's pretty easy. You now have an equation. And then you just simply plug in x a vector, and it will tell you the probability. Okay? The next one is called uniform distribution for the discrete case. The uniform distribution describes events that have multiple outcomes, but they're all equally likely. So they're kind of like categorical. But in categorical, you can't just assume they're all equally likely. But a uniform distribution, they are. So if you have a fair die, for example, then you'll be like 1 to 6, right? So the probability of uniform distribution is really easy. It's basically 1 over d, where d is just the number of categories, and that's it. So if you have six categories, then the probability is 1/6 then for everything. That's it. So notice there are no theta terms. Therefore, you know the probability distribution immediately. Just one over the number of categories. Well, when do you use uniform distribution? Well, uniform distribution could be discrete or continuous. Discrete is if you have like 1 through 6 as 6 categories. Uniform is more like time, right? Time. Well, so where, let's say you have a MBTA train from A to B, right? Where would the train break down between A to B? Well, let's say if it's equally likely to break down, then that would be a uniform distribution. And and the distance is continuous, right? So from A to B, the distance is continuous. So it can break down any one of these points. And also, another example would be what angle would the falling pin point towards? If you have a pin, it could point basically any direction and it's equally likely. And these directions, in terms of degrees, is also uniform distribution. Also, let's say you look at your watch at random time. What is the probability that the second hand will be between 0 and 10? So over here, if you look at your watch, it's equally likely that the second is going to be any time between 0 and 60. So then you can say, once you have that distribution, you can then calculate the probability. So remember, uniform distribution is 1 over b minus a. Okay, so this is uniform distribution. And then if you want to know the time between some value, between two values, alpha 1, alpha 2, then you can just take the area, which is really easy, right, to take the area for a uniform distribution. Notice